Hello and welcome to the lecture on the advantages of machine learning for mechanical engineering, and we're delighted that this lecture is held jointly with the Institution of Mechanical Engineers. Quick reminder of our previous lecture. We had a very successful event on nuclear technology with the Nuclear Institute, from large-scale reactors all the way down to the future of small modular reactors. Good attendance, excellent questions. Vote of thanks, Stuart Porterhouse. Closing remarks by myself. Our May Institute lecture is held jointly with the North East Coast Joint Branch of the Royal Institution of Naval Architects and the Institute of Marine Engineering, Science and Technology. And we look forward to welcoming Keith Hutchinson back to the Institute to talk about diamond mining offshore. We also have a in-person film screening produced by Hetton Colliery Railway 200. This film will cover the Hetton legacy. So do join us in person for that. If you want to find out more about our events, don't forget to follow us online, where we have an ever-growing back catalogue of lectures where you can enjoy. And we have plenty more events on offer as well, such as lectures such as the one you're attending now. We also have a range of conferences throughout the year. Our annual dinner, which attracts professional engineers and scientists from across the north of England, CPD and social events, as well as local field trips, hopefully international ones as well. The best way to support our work is, of course, through membership. There's plenty on offer, from postnominals, invitations to our events and dinners, discounts on field trips and publications, and of course the opportunity to get further involved with our work. So if you're interested, please visit mininginstitute.org.uk/membership, where you can download a membership application form today. And now I'll pass you back to Steve in Newcastle for the main lecture of the evening. Having dealt with neural networks during my PhD, I'm sure that this is going to be a very interesting talk indeed. But before we begin, we have a very special presentation, as Steve will explain.
So now we have another little event that we're squeezing in front of this, and it's my pleasure to introduce Hilary Bennison, who is going to give the Institute a miner's lamp in memory of Eric Wade, which is going to be received by our own Bill Bell. Thank you.
Myself and my colleagues here from the Open University, and we work very closely with Dr. Eric Wade, who was a member of this institute. He was a vice president for a year, and also, also he was involved in mining his whole life, from being a mining engineer through to he became eventually an academic, a social scientist, and a trade unionist. So we felt it was fitting. After he died, we had a collection amongst the Open University colleagues, and we raised enough money to purchase this lamp, which we would like to donate to the Institute. So thank you very much. I'll hand this over.
Well, on behalf of the Institute, thanks very much indeed. I knew Eric very well, and he was a great friend of mine, and he's sadly missed. We put the world to rights on many occasions and discussed all manner of things, and even to the extent we used to go to, on the anniversary of the Hartley Corrie disaster, we used to go to the shaft and sort of, you know, sounds fanciful, but commune with the ancestors. And yeah, there's some kind of sort of aura there, you know. It's if you're susceptible like we are, but so we can't do that anymore. But I'm sure Eric would have been really pleased at this, and thanks very much indeed.
Pleasure.
Thank you. Thank you.
Thanks.
Yes, put it on display. That's absolutely wonderful for us, and thank you very much, Bill. Very kind.
Well, you said it all.
Right, on to tonight's main event. We have the chair. I'm going to introduce Martin Smith, who's going to give us a talk on the principles, applications, and advantages of machine learning for mechanical engineering. Now, Dr. Martin Smith undertook his initial mechanical engineering training with GEC, Alstom, before embarking on a research career in engineering, thermodynamics, and green technologies, leading to a doctorate and postdoctoral work in electrical vehicle and high-efficiency engines. After his research career, Martin moved into strategic consultancy and gained extensive experience in the theory and application of machine learning. He has developed proprietary algorithms for machine learning applications in engineering and finance, which are currently being extended to applied conditions, monitoring, anomaly identification, and instrumentation. And on that point, I think I can ask Martin to come forward and give his presentation. Thank you very much indeed.
Hello, good evening. Quick question before I start. How many people here, if you could just raise your hand, are aware of differential calculus? And of those people, please keep your hands up, are interested in it to any degree. Right, here's my audience. Just before I start, obviously I've got a deep Pitmatic Northeast accent, although I've spent most of my career in London and the Midlands. I've never lost that. I'm quite severely dyslexic. So my dyslexia combined with Microsoft spell check often really turns into hilarious consequences. I've just realised just before coming here, I had to change opinion from onion to opinion. You are allowed to laugh, but not at my maths.
No.
Also, I'm not just a chartered engineer, I'm also a chartered investment analyst. So I occupy a fairly strange space between engineering and investment. So to the investment world, I'm the engineer who translates engineering jargon and vernacular into investment vernacular, and to the engineers and scientists, I'm the guy who gets them the money. Or used to, until the world ended. So that's what my kind of designation is. All right, then, really quickly, I'm going to try not to do a stupid thing where you stare at the screen too much. So just begin with, I'm going to cover off some professional views and caveats, because this is very opinionated and very personal, I hate to say. I'm going to discuss some of the vernacular around machine learning, discuss some background, probably more popular stuff in dispelling myths, and then there's going to be some quite deep stuff, not deep, some of this is extracted from an MSc module, but it's fairly pared down. The idea is to give you the sentiment and the sentiment and intuition behind machine learning, as opposed to it's a bluffer's guide. And we'll talk about some engineering applications, the risks, and where it might be going. So the first thing is, this is an entirely personal view. There are as many people out there who have a view on machine learning that think they know about it, and that includes me. There are multiple views. It is a very disparate, undefined, mad world out there, and there is no regulation, there's no institutions. And that's great. I often imagine where machine learning is now, or I'll use the word artificial intelligence once in this context, is where railways were in the 1840s. We're going through a sort of railway mania of machine learning right now, and who knows what's going to happen. And personally, I am an unrestricted techno geek. I believe there should be no restrictions on machine learning, and that's a fairly out there point. But hopefully as we go through this lecture, you'll understand how I come to that point of view, that machine learning really isn't what the media is making out to be. Okay then, some vernacular. Machine learning is not artificial intelligence. This is conflated a lot in the press and popular media. But we're going to use the word artificial intelligence just for a moment. There are two types of artificial intelligence. There's the science fiction artificial intelligence, like our friend Hal from 2001 and Skynet's Terminator and the Singularity and all those things that have been put under, is it the Corbin Project or for decades, centuries, there's been science fiction scare stories about some almost alien-esque artificial intelligence. And general artificial intelligence is a computer system that can equal or surpass a human being in cognitive reasoning and data analysis. This leads to possibilities of free will, self-awareness, and we're going to, if you get into that, you're into morals and doctrine and all sorts of. Fortunately, that's a bunch of dingoes' kidneys. It's not a realistic possibility, probably, I'm hoping, at least not in my lifetime. We're nowhere near it. For that to happen, there would have to be major advances in quantum computing and probably major changes in how we underlying theoretical underpinnings of machine learning, how we could use it. And later on, I'm going to demonstrate that what we think could be artificial intelligence is nowhere near it, using a toddler. What we do have, all of us, if you use YouTube, if you use Amazon, all of us use artificial intelligence to some degree every day. Now, what we have is narrow artificial intelligence, a specific algorithm or computer program designed to carry out one task and trained to carry out one task and nothing else. Examples of this are characterization, image processing and analysis, natural language processing. Now, there's a lot of stuff in the, I mean, it was even in the FT this morning about Bard with Google, chatbot, GT4, whatever it is this week. That comes under the term of, that comes under the term of natural language processing. We will not be talking about that too much in this lecture, but I do have some slides at the end. I would imagine there'd be a lot of interest in that. But we use it all the time. Now, I much prefer the term machine learning, partly because I'm a mechanical engineer, but I just feel it's more precise. Artificial intelligence gives connotations which are inappropriate. So for the purpose of this lecture, machine learning and now artificial intelligence are the same thing. Okay, and I'm going to just get rid of some background now, maybe it's a bit of fun. These are common myths, hyperbole and misconceptions when it comes to artificial intelligence stroke machine learning. These are things I hear all the time. These are things I hear in the press, that I hear from friends in the pub. And I'll just go through these really quickly. Nobody can tell what's going on inside of an AI. It's a black box. Dingo's kidneys. I know exactly how my models are working. I can inspect them. I think I know where this comes from, but it is a myth. Secondly, they learn all by themselves, are strange, evil things. Absolutely not. Most machine learning engineers spend the time torturing themselves, teaching these things how to learn. Deep learning neural networks mimic the human brain. Yes, sort of, but I'll come back to that. This one I particularly like. 38% of all jobs will be gone by 2035. Now, this stat permeates everywhere. It's like you can't read anything of a similar stat coming up. Where the stat came from, has anybody come across BBC Radio 4's More or Less programme? Excellent programme on stats. They once looked at this stat. I don't know if you saw that programme, sir? What they did, they worked out where that stat came from. And they went back through references and references and references and eventually found that statistic sitting in an MSc thesis from Sydney University. It then referenced an Australian government department's report. Not only did not the report not exist, the department didn't exist. It was a made-up reference by an MSc student that somehow is propagated and permeates way through. Nobody knows what's going to happen. Like in 1840, did anybody know what trains would do? Anybody actually think it wouldn't be working in 2023, but oops. There's no railway engineers here yet. The other thing is only mundane jobs will be replaced by machine learning. Actually, if I was a solicitor, I'd be bloody worried right now. As we go through, I'll demonstrate this. And then finally, the robots are coming well. Most of that's dingo kidneys. The robots will come eventually. I truly will hope that our robot overloads won't appear, just not during my career. The reason why we have these views are journalists, marketeers, futurologists, if anybody's came across a particular breed of people, I once had to manage one. Academics sensationalize things without understanding the core principles of them. I imagine back, I sort of recall back during the days of railway mania, people would think that you would die if you went faster than 30 miles an hour, because people just didn't understand the underlying engineering principles, the engineering technology, the maths behind it. And that's what was happening. Lots of people, futurologists and academics, who haven't got a clue and haven't invested the time, this is very controversial, I'm going to be in trouble for my colleagues here, who haven't invested the time or energy to understand how these things work, are merely writing articles in the FT and Looper and wherever you want, and it's dingoes. I'm not allowed to swear. I've been told not to swear. It's dingoes' kidneys. This leads to political and public misunderstandings, unrealistic expectations. People get scared. A bit more specific, there are problems with machine learning that we currently have in social media and our e-commerce systems, where we have confirmation bias in social media, creating echo chambers. Also, things like Bard and chatbots will ultimately are starting to lead to lowest common denominator issues. At the end, I'll discuss this about what might happen to the internet with all of this. And you might just have a world where all what happens, you have chatbots just speaking to each other with very little human interaction going on. You could have 80% of the internet just being automatically carried out with substandard machine learning algorithms talking to each other. A quick thing, this is a bit of an aside. As humans, we anthropomorphize things. We're taught as children that our teddy bears and toys have human characteristics. It's a natural thing for humans to do. When we see a computer or a program or a web page doing something uncannily human, we automatically anthropomorphize. Is that a word? We assign them human qualities. The machines aren't nearly anywhere near as good as our brains are projecting onto them. You know, they're not as intelligent as an ant. But so our brains are doing most of the work. AI, machine learning, is just pattern recognition. It's mimicry, sometimes good mimicry, but there's nothing special particularly about it. And as we go through this, hopefully I'm going to tone some of the technical stuff down, by the way, in this, although there is going to be some horrendous equations which I regret putting in. And I don't. I love teaching this stuff. Benefits of machine learning. We should see significant productivity improvements across all sectors of the economy. But that might also mean job losses. But when things change, things change. If it's managed, it should have benefits for all industries, and all branches of engineering can use this. Even though I am a bit of a techno fanboy with this stuff, at the same time, I'm an engineer, and I still treat this stuff with skepticism, and hopefully this will come out. An area where it's had quite early advances in medical diagnosis, in oncology. Turns out that relatively simple neural networks machine learning algorithms can identify tumours far better than a radiologist. And particularly, this is I'm going a bit of a side here, but whenever humans and machine learning algorithms work together, the productivity is levered and multiplied far more than just using machine learning algorithm over replacing somebody. IT threat detection, viruses, use that. Often we can use machine learning where we have engineering problems which would be too costly or impossible to do any other way. So machine vision, computer vision was a big problem for many decades. It's actually been relatively easily solved by machine learning and neural networks. An area I use machine learning quite a lot is code completion, where typing away, doing some code, doing some script, and then you can either use an applet to complete that piece of code, or you can even use a program where you say, I can't be bothered to write a for next loop. I want a for next loop that does this, and it's okay. But there are areas where it does work. One other quick thing here, I can't pronounce this guy's name, Arama's law. This is another artifact of, this law was invented in the 1970s, I think. So as humans, we think of the world as a linear thing. We see progression in technology in a linear way. And technology doesn't develop like that. It starts slowly. It accelerates, then reaches, what am I looking for? Tails off, an asymptote. Yeah. I would hate to think that the trains have probably gone backwards. So what tends to happen in the early days of any technology, people overestimate its impact. So do you remember all the stuff about the super information highway in the early 1990s and virtual reality? Well, quite doing it wrong again, that one there. So that's where those technologies were in the 1990s. Now, a good one is GPS. Yeah, GPS maybe was very, very interesting when it first came out, took a long time to get going. With GPS, we're now up here, we're doing things with GPS we never thought of. Question is, where is machine learning right now? And quite frankly, it's probably about here-ish somewhere. We don't know, okay? So, but the real long-term impacts of machine learning we will not see for a while. Right, I'm afraid it's going to get a bit dry now. This is where it's going to start sounding like an MSc lecture. An MSc lecture. I'll try and make it fairly painless. There are two broad categories of machine learning. And when I mean machine learning, I'm now talking about those narrow artificial intelligence algorithms. Supervised machine learning and, surprise, surprise, unsupervised machine learning. Supervised machine learning is where we train something, we teach something on a data set. Unsupervised learning is where we let an algorithm go mad on a data set and see what it comes up with. I'll explain this a bit later. In terms of supervised machine learning, which is going to take the bulk of this lecture, it has got some interesting areas such as classification of data, which can lead to things like quality assurance, anomaly detection, control systems. And also we're very good at multi-factor nonlinear regression, line fitting, and model predictions. So this is going to get a bit sort of more mechanical engineering as we go through. But basically, we can use supervised or unsupervised learning where we train or we don't train, and we can use various techniques to classify objects. Is it a train or a car? Is it a bearing or a seal? Or we can use things to make predictions and complete models. Right, there are three commonly used techniques with machine learning. The first one is random forest. It sounds like a football team when you think about it. This technique, I'm not going to go too much detail about this, but it's a technique which derives lots of random decision trees. It's used a lot in the financial sector because it's got similarities with binomial, I believe, but it's got a lot of similarities with binomial stock options analysis. Plus, it is a bit of a black box, and it's very easy to people to pour data into and not really understand what's happening. So a lot of financial analysts, lazy buggers, use it. I personally think it has some problems. From a personal point of view, I don't think it's particularly elegant as an engineering solution. But it is a valid technique that is used and produces reasonable results in the right areas. Another area is an awful name, the support vector machine. It sounds a lot more sexy than it actually is. It's a geometric approach to categorizing data. It's particularly good when you haven't got much data. It's used a lot in e-commerce. So the place you will see is in an Amazon recommendation list. So if you've looked at 3 albums by Queen, it'll start recommending albums by Queen and Alden Stardust or something. They are the two-stroke engines of the machine learning world. They're quick and they're dirty, but they work reasonably well, but they're not that refined. Well, that's my personal view. When most people think, well, the most common in common vernacular, what people really think of when they think of artificial intelligence, machine learning, deep artificial intelligence, is neural networks. And this is what the bulk of this lecture is going to be about, or the remains of it. So, without further ado, I'm sorry, the maths is going to begin. This is the most simple type of neural network, where you have two inputs, a node where some maths happens, and an answer comes out. That's a bit like a NOAND gate, basically. That's basic. Neural networks are just lots of NOAND gates. And I mean, we could just stop the lecture there if you wanted. Right, there's nothing mysterious, nothing unearthly about that, except if you're a journalist and don't understand what a NOAND gate is. So you put data in, a node happens where some maths happens, and you get an answer out. That is a neural network. The neural network, the answer depends on these two constants here, where you have data coming from your input nodes and then is somehow affected by a constant. And each piece of data has some constant attached to it. The data going in can be all sorts. It can be a Boolean, it can be an integer, it can be a float. It's a number. Now, this is where the maths happens. Now, this piece of maths here, some of you recognize this as the logistical regression formula. This is usually what's embedded in the node. There are other species of it, but for the sake of this lecture, this is what we use. Now, the theta and the x are the totals of... sorry, I'll move it to the next slide because it shows it. So the constants, those thetas, and the input data, the x's, are what appears in the bottom term of that function there. If you're sucker for punishment and you enjoy maths, that is the curve that gives. That's the logistical regression curve, or sigma curve. One of the reasons why we use that for is it's very good at making decisions. Because of that inflection, that near vertical inflection, you either get a 1 or 0 depending on the data you're putting in. So it's a very good discriminator. Now the trouble is with machine learning, okay, so we have some data, we're getting an answer out. But what we want to do is train that neural network, that very, very simple neural network, to tell us when we've got some data we've never seen before, is it a 1, is it a 0, is it a cat, is it a mouse? So what we've got to do is inform the neural network what these constants are to give you the desired answer. So what we have is a known output, and we have known inputs. We then optimize those constants there. So next time we have similar inputs, it produces a similar output to the known output. Again, that's neural network training, and you know it all now. Who wants to go to the pub? I'm afraid not. So an example would be if we had x1 and x2 being 1, we had our thetas as 1, we'd have 1 as an output. We put zeros in there, we would have, I mean, this is where it concerns from the NOAND gate, basically. One other complication, what I wasn't showing you, and this is more for completeness and a bit technical, all neural networks, all nodes have this thing here called a bias unit. That's like a damper on the maths. It allows you to dampen down or filter any extreme behavior in these two inputs. They're not normally shown on neural networks. I won't be showing them again, but it's just in case any smart bugger decided to say where's your bias unit gone to. Okay, this has come back to one of misnomers. Obviously, these are human mammalian neurons with axons. So basically, the analogy is these are your inputs. This is what's happening in node, and this is your output. It's more by but neural networks, it's probably fair to say, but they weren't inspired by, probably weren't even informed, but they're certainly not trying to mimic the human brain, although that's in common parlance. So, okay, but there may have been some inspiration there. I'm not going to go into the history of neural networks, machine learning, that's like 2 lectures in itself. So you might have multiple nodes. So we might have multiple data inputs. That number down there might be measured in the millions. There might be dozens of nodes here, but they'll all feed into each other to give you your answer at the back out here. Now, just to move on further, what you will then find is that logistical regression, that sigmoid function is now embedded in all functions. So all the functions see it and feed forward. That's called forward propagation. If you've got all your features set up right, it will then the data will propagate forward to give you theoretically your desired answer. And each of those so for each one of these lines, there is a separate feature, there's a separate constant, a parameter. So one of the things that machine learning is all about finding out how you derive those parameters. And I'm going to hopefully do that without too much pain in a minute. People can leave now if they want to. There's going to be equations. There's going to be differential calculus. In reality, you can sometimes end up with thousands, if not millions, of these parameters. And this is why machine learning can be computationally very expensive. So we have some, this is just because I can't be bothered to draw circles and lines anymore. You have a lot of inputs, you have a lot of unknown constants, you have your activations, that's in different, in those nodes, sorry, the nodes are often called activations, so these nodes are sometimes referred to as activations. And you get a known output. Now, what we're doing here is we're training, so we have some known inputs here, we're putting in, and we have a known output. We need a way of deriving what these constants are to give us our known output. And as I said, you may have literally thousands of inputs for any one for any one application. Now this is derived through a thing. What we're trying to do mathematically. So I'm going to try and limit these terms. But at the heart of machine learning, there's a thing called the cost function. And that is the difference between the answer you want and the answer you're getting. And we use differential calculus to minimize that difference as we're training a neural network. Does that sort of make some intuitive sense? Yep. Right, that is the equation you need to calculate the difference. That is the piece of differential calculus that is the most effective way we have got to calculating all these inputs, and I will not go through that once. It's only been put up to scare people. I use it to scare clients away and stuff like that. So to give it some more real sense now, I'm going to use some real world, a slightly flippant real world application. We want to train a neural network to classify the difference between cats and dogs. So, okay, how do we do that? Well, we acquire a large amount of images which are labeled cats and dogs. Correctly, by the way, each cat is called a cat, each dog is called a dog. And we feed each of those images into a neural network we've designed. And we tell the neural network, is it a cat or is it a dog? And then we run through this training set, and the backpropagation algorithm will derive the best fit of those parameters to give us the answer we want. So I'm going to do another example which should explain this. And then we have more data so we're going to show a neural network lots and lots of pictures of cats and dogs, tell them it's a cat or a dog, and those parameters will be optimized to classify what is a cat or a dog. This is where basically this is most complicated and confusing it gets. And then we derive a best fit for the neural network's parameters, and then we can test it on some validation data. Right then. So we have a dog. So we're deciding that dogs are all going to be called, so in our model, dogs are going to be ones, cats are going to be zeros. We can tell who's cat and dog people here by this method. So how do we do this in practice? Well, what we do, we break the picture up into groups of pixels. I mean, this is big pixels. Obviously, in reality, we only make 3 or 4 pixels, or even individual pixels. And then what we do is we feed those pixels into a matrix, into those X's I showed you earlier, bit by bit. And then we tell the algorithm at the end, it's a dog. The data we're feeding, if it was a black and white image, it would just be the intensity of brightness. If it was a color image, we'd just feed in the number of bits for the red, blue, green. But it's a fairly simple thing for a computer to do, to take apart an image and just represent it as a vector of numbers that represent that image. But we tell it's a dog. And then what we do that for literally thousands of cats and dogs. Literally thousands. And what we do is that each time it sees a cat or a dog, we feed it into our neural network, we run this algorithm on it, and eventually, after we've gone through hundreds, thousands, tens of thousands of cats and dogs, we end up with an optimal model that when we feed it a picture of a cat, it will say 0. If we feed a picture of a dog, it will usually go 1. It should go woof, shouldn't it? Sorry, that was a really bad joke. I completely lost my plot. I'm going to go back to the picture of a dog in a minute because there's some interesting... I'll do it now. What we're really doing with this is we're trying to find features. What's really happening is we're trying to recognize features, pick out things, patterns within that picture. Now, I'll come back to why cats and dogs are important for later. But it turns out when you do a cat or a dog discriminator, what ends up happening, you end up with 2 things, either a floppy ear detector or a nose detector. What happens is a neural network actually concentrates on will detect the dog's nose if it's a dog. What would actually happen here is cats have peaked ears mostly. So if you didn't, so you could get miscategorization of a Western Highland Terrier as a cat through a poorly trained neural network. Sorry, I don't know why I went down that particular rabbit hole for. Also, you might just not have cats or dogs. You might have cats, dogs, and mice. You might have 3 categories. So well, how we deal with that is just not ones and zeros. We have 3 output nodes. And how each output node knows which one it is, it's a 1 with the highest number at the end. And so I hope this is still making sense to people by and large. There will be more pictures of cats and dogs later. So how do we really use this? The cats and dogs thing is a bit flippant, but some excellent applications. Well, condition monitoring. A lot of my work I do is looking at, for instance, bearings and gearboxes, using machine learning to detect when something is going wrong in a gearbox. You have an imminent failure. Another excellent place for this is in production quality assurance, looking for cracks in things. Looking for, first of all, you could imagine taking a camera over some rails and detecting a crack visually on what sort of crack it is. You could use it on production lines, what's in tolerance, what isn't tolerance, what's acceptable. And I'm going to come back to this example in a minute, but autonomous vehicles. Autonomous vehicles have to have lots of machine learning in them, but one of them things a vision collidance. Right, this is where I use machine learning quite a lot, and with my work with investment algorithms and also in engineering applications, is time series analysis. So we've gone away from categorizing difference in cats and dogs, and we're now trying to understand a function, some data. Now, it's actually really quite simple. What we do is we just break up that data. into a window of data. So we select some data and we break that data up into little elements, and we feed those elements into a neural network, and then the last element in our window is the answer, is the expected result. And we just move through our data set and move our data set along one element at a time, and we then can train a neural network basically to perform non-linear, and if we need to, multi-factor, to perform a non-linear multi-factor regression. Which, now we do have tools that are particularly the fast Fourier transform, for instance, but this can work in certain areas which I'll come back to. It's actually a relatively simple process. And then what happens, we do the backpropagation and we end up with the with the constants in there, and the output this time isn't a yes or no, it's a number. We can use it to perform, and it's actually quite it's quite a powerful technique. So this is sunspot modelling. So I've got to get the right one. It is the blue line is the actual real sunspot data. You know, is it 7 years of sunspot cycle? So that's a relatively simple neural network. This is taken from a standard sort of exam test. It's another one of those standard machine learning things, examples, tutorials. This is done with a relatively simple neural network where we've looked at the raw data and we've came up with a neural network that we feed a piece of X data in, and it will give us the Y data. Now, okay, that's sort of okay. I can live with that. You probably couldn't model sunspots any other way. This is empirical modelling, obviously. So, in terms of, say, it's a stock market analysis, this is the sort of thing that people will come up with. So where would you use this? So where you've got complex non-linear behaviour. And as I said, my area is particularly good where you have cyclic and semi-cyclic systems with some degree of, I know I'm just reading this out now, some degree of variation. So an example of that would be, say, a bearing running in a gearbox. It's fairly predictable behaviour, but there's variation in terms of temperature, pressure, of speed, and of wear. That's a sort of good application. Also, systems which are too hard to model through a conventional or qualitative means. Particularly good at anomaly detection or failure. And noise reduction, if you have a very noisy, and I mean noisy, I mean in terms of an electrical signal or an input signal. If you want to make your fortune, try and find a good way of getting a good signal to noise ratio analysis for the guys in the city. You know, then they'll kill you. And also in control systems. But it's a very, very powerful technique. Now, this is where the nitty-gritty stuff, more nitty-gritty. To train a neural network, you may need literally tens, in some cases, hundreds of thousands of pieces of data. And therefore can be very, very expensive. Because somebody's got to sit there and go, cat, cat, dog, dog, cat, cat, dog. As an aside, a lot of people are employed, particularly in emerging economies, to do this. And this leads to bias and problems where you have people, low-wage people who aren't really engaged, categorizing things to provide label data for people like Google and Meta. No, that's Facebook. And often that data can be biased. People aren't engaged with it very much. So, so you need lots and lots of data. If you have a limited data set, you will overfit. If all you've got is pictures of labradoodles, it will think every dog is a labradoodle, except when it sees a terrier and think it's a cat. It's like any form of fitting, through any form of regression, we can overfit something. Because if you overfit your data set, your training set, it will not generalize to the real world. and you want a bit of slack in that, to be perfectly honest. However, as engineers, we are in control of our own system. So when it comes to gearboxes, bearings, turbine shafts, rotor hubs, they're a control system. So for us, it's easy to get data. It's not like social media or anything like that. And we do have predictable systems. When it comes to, this is a really important point, when you have your 20,000 pictures of cats and dogs, you use 70% to train your data on, and you use about 20% by, I'm going to have that done properly, haven't I? But 20% used to test on. If then it doesn't generalize or work well in your test set, you start again, you design a new network. You always leave a bit of data for when you've met your criteria, you're happy that your neural networks working correctly, that you validate on. So, and one of the biggest expenses is I mean, it's often said that that machine learning depends on large data sets, and therefore the companies that can afford to do it are going to win. I don't personally think that's the case, because this stuff is so accessible. Right, where am I to now? Yes, overfitting. This is, again, one of the biggest problems where we overfit, we overtrain a neural network to a specific, we don't use our data properly, it's overfitted to the test set. This will generate a lot of false positives, or in some cases false negatives, which is something you don't want in oncology, for instance. It's caused by limited data set and bias in the data set. This might be a bit apocryphal, but there was something a couple of years ago where when people were in the United States looking at people of colour were more likely to be accused of crime by machine learning predictive systems, because the photographs of people put in who didn't commit crime were white. So it created a bias. So the thing is, I mean, another example is that most of the dogs in the world, I'm going to use dogs again, most of the dogs in the world seem to be Labradoodles. If you trained a neural network to detect different cats or dogs, it would say a lot, it would bias toward Labradoodles. It would never detect, it would think a terrier was a cat, for instance. It's a bit of an arcane point, but also complexities in neural networks. When people in the press or popular see neural networks, they see this ridiculous thing here, that would overfit. If you make a neural network too complex and too precise, it might not even be stable, it might not even train properly, and specifically it would overfit. In the real world, as simple as a neural network can be, the better. So the best models are actually often the simplest. I'm not going to go into this too much, but what I've showed you is a very vanilla base model of a neural network. There are tens of thousands of PhD students in maths right now coming up with new bits of maths to put into those nodes. And I'm not going to bother going through them because they're really quite complicated. But it's just different types of maths to try and generalize and stop overfitting. Right, I'm gonna just go back to cats and dogs. The reason I was talking about cats and dogs it has been a standard machine learning competition for decades now. So in machine learning world, there are certain competitions. So cats versus dogs is there's a website called Kaggle which has lots of data. It's a bit of a playground for machine learning buffs, and you design your neural network and you can see where you're on the rankings. Cats and dogs is one of the standard data sets, one of the standard competitions. So cats and dogs has been around for well over 10 years. It has 20,000 labels. It gives an accuracy of nearly 99%. Great, that's fantastic. Yeah, okay, bloody brilliant. It might take several hours to train on a powerful computer. I've got a grandniece. She's 18 months old and she has seen a picture of a cat and a dog in a book, and she can now tell the difference between cats and dogs without any more training at 100% accuracy with a data set of 2. Why is 99% good for? why do engineers jump them down? I mean, I do get excited about it, quite frankly. But as I was saying before, that this is why our current technology, machine learning, or whatever you want to call it, is nowhere near what the human mind does. So, predictions of impending robot overlordship, Dingo's kidneys. If my 18-month-old niece, 20-month, can do that, then yeah, you take my point. It's not as good as it looks. Now, there's a real-world application for this. Now, this is a bit flippant, but sadly, it may become true. So let's have a scenario. How many times a year does a toddler run into a road in the UK? 10,000, 100,000 times? Now, the cats and dogs algorithm competition has been going for 10 years. It's got a great data set. It's the best we've got in some places, yet it's only 1% accurate. If 100,000 times a year, a toddler runs into a road, and the algorithm can't decide whether it's a chicken, a pheasant, or a toddler, 100 toddlers a year are going to be run over. Now, I could speculate that's one of the reasons why we don't have self-driving cars right now because, I mean, self-driving cars, the core technology works brilliantly. Fine on the motorway, and great for trains, but I wouldn't want that to be my great niece. So even though that 1% looks great, in the real world, 100 toddlers get run over. And toddlers do walk and sometimes look like pheasants in the distance. Well, certainly the toddlers are, no. Right, sorry. So in terms of applications, so just to go back, in our sunspot prediction, we had a 14% error. Now, it's a complex natural system that's very hard to model. You know, I'll live with that 14%. I couldn't probably get any better. If I did astrophysics models, would get nowhere near that from first principles. But modeling a predicted, well-understood system, I wouldn't accept that. I would use Laplace transforms. I'd use a Fourier transform. There's plenty of a way. I would use just vanilla regression if I want to do that. Anything where you've got a complex system prone to noise and vibration, where you want to get rid of that noise, find a signal is a good place for it. So I say gearboxes, compressor plant, helicopter rotor heads. This is a bit of plug for my work. In those applications, you can get, like, I'm now looking at 1 part per 1,000 for that detection within a, within a controlled and designed system. I'm not going to go into too much, but obviously there is a difference between accuracy and precision. You can be very precise, but you can still be very wrong with that precision. And in any form of modeling, that still happens in machine learning. But an interesting thing is machine learning is very good at handling ambiguities and uncertainties in the way that other bits of modeling and maths can't. Because of, like, almost having a mathematical tolerance within the network. That might not be precise, but they're pretty good at handling ambiguity. And this is sometimes where we think they're magic for. You know, I really wanted that Queen album, you know. And that can be uncanny, but this is where the ambiguity works quite well. I'm only putting this a couple of slides in for completeness now. That looks hideous. It's very rare in areas such as vision, computer vision, or in natural language processing, that anybody will come up with their own neural network from scratch. We use pre-trained networks. So large large research projects will derive the front end of a neural network. It'll be incredibly complicated, sometimes dozens of layers, and all we do at the back end is clag all a little bit on in the end. because these networks have been pre-trained on millions of applications, of instances. ChatGPT-4 bot, whatever it's called, is one of them. I'll explain that if you ever need to. So all I'm going to get a point across is pre-trained networks is where you take somebody else's network and you just add a little bit to the end, or you cut bits out. It's like a modular approach. Most of them are shareware and free to use. Very quickly, edge computing. Now, we've got, no, I've got one with us. We now have single chip computers, microcontrollers, as powerful as a PC I did my PhD on in the 1990s, which I find quite scary and sexy at the same time. These are capable of running neural networks and carrying out in situ embedded analysis. So, for instance, you could have one of these embedded within a gearbox or even a single bearing to say, right, this bearing's burning out. It's going to burn out in so much time. And that data can, but these things aren't powerful enough to train their own models. The models have to be trained on a central server, and then that pre-trained model has to be embedded into that device. I'm sure I have one somewhere. Yes, so this is something we're talking about. Running out of time here. So we're talking about something like that. This is like £3.50. Cheap enough, it's actually even got an analog digital converter in it, so you can just, so you can have these devices which are effectively the cost of computation is zero, and you can have them embedded in just about anything. You're getting into the, I don't like using the term, but the Internet of Things. So you could imagine you could have a train. Within that train, you could have a single board computer, an embedded computer, within the bogie, within the gearbox, within the motor, within the inverter, monitoring that. It's trained with a neural network that allows it to identify maintenance problems or performance issues. That can be reported back to a local technician operator, but at the same time, the device can communicate with central powerful servers that then train it. So the term edge computing is that you put intelligence on the edge of the system, but you rely on central processing to train models. Sorry, again, it's just to make sure for completeness. I'd missed a slide. Sorry. Oh no, I've got it. No, it is back. Just really quickly, nobody writes their own code anymore. Back in the day, I used to try and write this stuff in C and MATLAB. Now there are APIs, there are programming languages that use Python, and you don't have to code up your own algorithms anymore. You just call functions within Python. There are three major ones: PyTorch, which is Facebook, an independent one, and the one which I use is a thing called TensorFlow, which is done by Google. This is more, and if like practice engineers want to embed this stuff, I would recommend you would start using TensorFlow because it's designed for production and distribution. I won't go into the rest of the technical details there. Just for interest, that is what machine learning code looks like in the flesh. It's not as scary as it looks. This bit here is us taking in the data. This is a time series now. So this is us taking the window of data in from that of our sunspots. It's feeding it into two layers of a neural network. We've got 64 nodes in each layer, and it's just spitting out an answer at the end. And that thing there just becomes an object that holds the data. Like, that's it. You know, that compared to how it was like 10 years ago, writing all sorts of code is a lot easier. So it is very accessible, and this is all free. You don't have to, you know, it's freeware licenses, all this stuff. Another area is unsupervised learning, where a computer isn't trained, and typically it's good for clustering. If anybody remembers the K-means algorithm, it's been around for probably about 150 years. It's a way of grouping things, so a computer can group and classify data without being trained, and multivariate Gaussian distribution, which is again just a standard inferential technique. People call this machine learning. I just want to bring it in for completeness because it is used quite a lot. Okay, so future developments. First thing is I have a commercial interest and I'm biased. Second thing is it's inadvisable to predict the future. I have a stack of books from my childhood home saying I should be holidaying on the moon right now. But my personal thing, that's my lecture up. My personal view is that embedded within the engineering world, embedded machine learning could have a lot of potential. And I'm working with a local university, but we may be what a very sort of like ambitious goal may be. Can we eliminate planned maintenance using machine learning from non-safety critical systems? As I said, they're very good in systems where you handle ambiguity. Another interesting approach is using machine learning to deal with ambiguity and uncertainties in conventional analysis. So here's a thermal decay curve. The big problem is how on earth do you model that bit at the end? Well, we can apply a neural network in there to deal with the ambiguities and variations and uncertainty would normally have with a thermal decay curve caused by convections or different ambient conditions. If you're interested, I'll put this in the slides, there's some, future developments longer term will be new tools, new architecture, but particularly quantum computing could be a game changer, but again, that could be years off. Right, just sort of in conclusion, now machine learning methods can be very effective in engineering applications. But the thing is, machine learning is just another analytical method, just the same as fast Fourier transform, is just the same as Laplace transform, is just the same as regression. It's where to use it effectively. It's not always effective and appropriate, and it requires a lot of good data. And this data can be subject to bias. And as I said, do not believe the hyperbole and the dingo's kidneys of the futurologists and whatever's in the FT or the Guardian or the Daily Mail this morning about the impending robot invasion. If anybody wants to, if anybody's mad, there's some excellent courses on Coursera which start you from a very basic level up to being a certified TensorFlow Google engineer. I'll send you the deals. I don't know, yeah. But these are done by a guy called Andrew Negg, who's probably like one of the machine learning gods of this world. I'm sorry that was probably a bit of a bit over ambitious. Right, who wants to torture us? I do have extra slides.
Right, well, if you thought what you were saying on things being futuristic, that was futuristic of me, I've got to say.
Just no AND gates, just lots of them.
Yeah, exactly.
Nothing clever about it. We're engineers, we can't do anything clever.
I don't believe that. Right, everyone, if there's any questions, could you please state who you are and what organisation you may be with?
I'll let that. Well, it's a question of a comment, actually. You talked about plan maintenance.
Aye.
On the machine. This has always been a source point going back many years in the mining industry. Lots of the bosses always thought we could do away with plan maintenance.
I know.
And the thing that we cut that out, we could have over time. You see, you don't need a tech person to put these right. Yeah, and it just reminds me, and it's 40 years ago, in the 1980s, when we introduced oil debris analysis, shock pulse monitoring, and vibration monitoring. It doesn't seem to have come that far.
Well,
in 40 years.
The caveat there is it's a BHAG, it's a big, hairy, audacious goal. Yeah. I'll be perfectly honest, it's the sort of thing that gets the attention of funders.
I see.
And as I did my initial training in the nuclear industry, and boy, will not want to get rid of plant maintenance fair.
I mean, we put the gear on all kinds of gearboxes, motors, drums, etc. Certainly didn't put them on helicopter rotary gearboxes, which are, is very important. But the changes that we could actually make and predict we saved quite a lot of money in production.
Yeah.
And I was just, it just looks as though those ideas of putting one of those digital monitors on, I think, is absolutely fantastic.
So
I wish we could have had them 40 years
well,
ago.
the difference is that you would be using a neural network specifically. So say you had a hydraulic ram. You would measure, say, over a very high data rate, and I'm just meaning as I go along, you would measure variations in the pressure as that ram extended. Any variations, which even very slight, might indicate a seal going, may indicate cavitation, may indicate a pump having a problem. The speed you can, and then what you would do is say, well, actually, if we see this type of resonance or this type of pressure variation, we know it's a seal going to go. Yeah. And that's what you would train the neural network to do that, and it would just come on your phone saying, seal number 7 going, get out of the pit before it's about to collapse.
My assistant engineer and 3 of the craftsmen with him, he could go around and he could predict when gearboxes were going to go. Because they learned
noise, whirring.
And they sampled the oil.
Yep.
And they could monitor that oil over a period. And the first thing I ever did, change the oil at the weekend.
I could do that on my old Triumph Spitfire gearbox.
And, it worked.
Just because it would go every 6,000 miles anyway.
Yeah. I think gearboxes are built to be better now.
What Stuart's saying is he's gathering the data there.
Yes.
That's right, that's all it was.
And so what you'd be doing...
We kept charts in the plan maintenance, so we kept charts of each gearbox.
Yeah.
So what you would do is then that intuition, that knowledge would be embedded into the neural network, then put onto a chip in. However, but that does mean jobs.
Well, there's nothing wrong with giving people jobs. Because there's a cost involved when they're sat and you haven't got a job. We did it with the service compressors.
Yep.
We had 4 men that used to come in looking after service compressors. We monitored them, we put all kinds of equipment on, and we had 1 man would start it on a Sunday night at 10 o'clock, and nobody would touch it, and we'd just be monitored in a control room. So we sacked 4 people. Now, the cost of, what happened to those 4 people? How much does it cost to keep them alive and feed the families and pay the mortgages for the next God knows how many years?
As an interesting aside, of course it would be the French, it's the French, are looking at ways of making machine learning algorithms pay national insurance. That is very French, but actually quite clever.
Will they get a pension at the end as well?
Probably, and I'll get it when I've been around for like 55 months, or when a new version of Windows comes out.
That's the French. Trying to get them into work.
Won't they have to wait until the devices are 66 years old?
Yes, I was going to say yes.
Any more questions, please? Anyone? Yes.
Nothing to do with your lecture, actually, but you don't like the word artificial intelligence. No.
Yeah.
But in the paper today, or media, the last couple of days, have you read about the Michael Schumacher incident, where a German magazine used AI to simulate an interview
Yes.
with Michael Schumacher, although, as you know, he had an accident, a skiing accident 10 years ago, and has been basically, I wouldn't say vegetable, but, you know, uncommunicative. And this is creating all sorts of furores about the use of artificial intelligence. So this, I suppose, is a bad...
Oh, yes, it absolutely. Well, I've got a slide. Can I just show another slide?
Yeah, sure.
So, because I knew someone was going to ask this. Natural language, now, it's not a big engineering topic. So that's why I admitted it for, but it's how all these things like virtual Michael Schumachers and chatbots work. Okay, we take a lineup, oh, Brave New World with such people in it. And each of those words is just another piece of data. It's just like a pixel in the Westie. It's just like a piece of data in our sunspot. Well, that just represents a piece of data. We can put that through a neural network, and we can learn patterns. So for instance, such and people probably come quite a lot together. There's a mathematical technique called an embedding. I'm not going to go into this, but it's basically Euclidean distance between different words. So you might have a 16-dimensional phase space that you map words onto, and you look at how close those words are together. Here's a 2D representation. So you find travel and food are very close together in some phase space. This is then used to derive the constants, those parameters in a neural network. And this is the basis of, so what somebody's done, they've just taken everything that Michael Schumacher has ever said, learned his speech processes, and the sentiment within those speech processes, and they just started it. And what they've done, they've just fed in a few kernel words to start with, saying, you know, my life as a racing driver, and it carries on and carries on. Now, it's a bit of a parlor trick, this. Let's go backwards. So it's a bit of it's mimicry. So again, one of the standard things, if you're getting into machine learning, if you do one of those courses, you write a neural network to mimic Shakespeare, and it is frighteningly easy. It's easy, and it looks great for the first sentence. After 10 sentences later on, it's just garbage. But that sort of simple, single, couple of layers neural network. Chatbot GT4 has got literally thousands of layers. So that's how that works. So again, it's nothing special. It won't feel special, but Michael Schumacher's talking to us from a coma. It's just mimicry. It's good mimicry. Now, I'm just going to, if you don't mind carrying on with this. As I said to you, a neural network, you have to tell it what the right answer is. So when you use a chatbot, and this is going to become a bit of a problem in academia for marking things, or you know, I'm going to come back to an excellent example in a minute. But if that journalist, so that journalist probably generated hundreds of different interviews, and one of them sounded right, and he said, that's right. The network, the neural network's got, he likes that, and then you build up that bias, and that's how you get your echo, as a bit of a leap, that's how you get your echo chambers. And there's an interesting artifact happening, that there's evidence to show that the neural networks are now training us in recommender systems. That a neural network, or not actually a support vector machine on YouTube, will get used to the things you like, and then you start liking the things it's showing you, so it's almost being reversed. Now, so these are going to be some of the real problems. So you could imagine a world where you have chatbots. So, for instance, I'm sending you an email, and I'm saying, I've got a great idea for a new floggle toggle. And you go, oh, not Smithy again. And you just say to your computer, any more emails from Smithy, just send a nice reply, sound like from me, we'll talk later. My chatbot goes, great, when we're going to meet. And then suddenly this conversation starts happening. And it gets more and more absurd because you're getting further and further down that prediction level. And it's one of the dangers that the internet might be 80% full of just chatbots talking rubbish to each other eventually. But in the meantime, it can have real problems with bias as well. Sorry, I went off on one there.
Anyone else? No? Oh, yes.
Taking that point and moving that onwards,
Yeah.
right, you can perhaps understand why people are getting concerned about where we're going with all of this. Okay? Mm-hmm. Now, you're right about, you know, social media.
I'm going to meet, yeah.
But it's fascinating, and you know, it's way over my head here, right? And I'm 6 foot, but it's, you know, it's way over there. But it's, what are we going to get out of it as a society?
Right, okay.
Right? Are we going to get cheaper products? Are we going to get more money in output? Are we going to get a better quality of life? You know, I mean, those are the things that for me, right, are important, right? And also, I think, the fact that at this point in time, people are saying, AI, well, that's going to take over the world. And I accept all of that, and I accept what you're saying. But the very fact that you're saying that your computer is speaking to Dave's computer, you know, and you don't even know what the hell's happening, right? Gives that sort of feeling.
Yeah, so can I give you two answers to that? The first one's a little bit flippant. I'm an engineer. The things I'm interested in, I'm not interested in chatbots. I'm interested in time series analysis or bearing failure. So part of the answer I want to give is like, well, I don't really care because like this is the stuff I really think will have an impact. And the real impact there will be the positive. So this is just a personal view. So the impacts will be, I mean, already machine learning's had a decent impact. It will mean that cars are more reliable. Hopefully they won't run over toddlers, just chickens. Things will get cheaper. People will be more productive. I don't really think many people will lose their jobs through machine learning, but they'll use machine learning as a tool and increase their productivity. People might have more interesting jobs. I really can't see self-driving cars being a particular thing in any future, so not even the taxi drivers are going to lose jobs. I could be proven wrong. But the thing is that there are lots of little incremental improvements that can happen. And we won't, like mobile telephones, like we don't even notice them anymore. That's a sort of little spreadsheets. Things that small incremental changes across a lot of industries will just totalize to a big actress. I'm trying to think of a word. However, the ever downside, and this is just my opinion. I've got no evidence. It's actually not. It's just complete subjection. We'll get used to it. We'll get bored of it. So journalists as engineers, we've always known how to do a linear regression. You know, we know how to use Fourier transforms. To us, this is just another technique. But to a journalist never had the equivalent of regression. Suddenly, it's magic. I can tell to write an article about Michael Schumacher. Oh, there it is. It's new. It's like the train. It's like the railway mania. And after a while, we'll get used to it, and we'll think, wow, it's a bloody chat. I'm not going to answer Smithy because he's just sent me a chatbot. And I'm not quite sure what the answer is, but my gut feeling, it will get old very quickly. And the amount of people who are not engineers, who couldn't understand the differential equation if it fell on their head, people I know in the technology and investment community are suddenly all about this chatbot 4 thing, whatever you call it. I'm just saying it's just like, you know, but trying to jump on a bandwagon that's already left, and it's going to get old quickly. That's my personal view. I could be sitting here in a year's time apologising to you as our robot overlord tells us we can't go to the pub. But yes, just as an aside, this dreadful thing here, that is using a artificial intelligence machine learning art generator. I typed in the words mechanical engineering, bearings, gears, neural networks. And it came up with a Geiger-esque monstrosity. And that's the best. That's after about 20 of them, by the way. And in a way, that sort of sums up to me what the non-precise, non-engineering social applications of machine learning. It'll be a bit, yeah, it's okay. So just one last thing. So chatbot GT4, a lot of people in the coding community use the complete code with. The answers are sort of okay, but it can't solve anything particularly complex. I mean, that might change in the future, but it will get old quickly, and I think, and just as human beings will learn to differentiate it. And I'm sure there'll be legislation as well. What will be quite interesting, and you can actually do this, is to write neural network machine learning solutions to identify when a machine learning solution is talking to you. You know, you can get face generators. Well, there are ways of actually spotting if something's been artificially generated. So if you can detect patterns, if you can create patterns, you can detect patterns. So I'm not quite sure that went anywhere. So that's well.
Okay. And lastly, if you're still looking for that Spitfire gearbox, there's one in the back of my garage.
Is there?
Yeah.
Is there an overdrive? No. Oh, we're not interested.
Hi, interestingly enough, I've had an remember Willie Whitelaw.
Oh,
of
yes.
distant memory. He was Minister for Technology in the 70s, I think. And he came on TV and said, the microchip. It's the brave new world. It's the future. We'll all get things for cheaper prices. We'll have to learn. We'll only be working 3 days a week. We'll have to learn to do something with our leisure time. You know, all this is going to change markedly. Did it?
There's a very good, if you go on YouTube, right, there's a, remember, there's BBC, I don't have a TV, does BBC Horizon still happen?
Occasionally, I think.
If you look for it, there's a 1978, 1979 episode of Horizon called The Chips Are Down, which is exactly that thing. It's talking about, it's introducing to people that computers are suddenly happening, and it's not Willie Whitelaw, it might be Tony Benn talking about how to respond to it. So it's worth having a look at, because with 40 years, it's quite interesting to see what hasn't happened.
Hasn't happened, yes, interesting. Thanks.
Right, well, thank you very much, everyone.
Sorry that went a bit too long.
Oh, no, not at all. People ask questions and you're giving good answers, Martin. That's the essence of it. Thank you very much indeed. Now, can I call on Phil Hartley to give a vote of thanks on behalf of us here at the Institute?
Ladies and gentlemen, I think it's been absolutely fascinating, so I would like to propose a vote of thanks to our speaker this evening.
Thank you.